Good evening, students. Am I audible?
Yes, sir.
Okay. See, I told you there is one subtopic pending in electromagnetic waves, right? I just checked the syllabus again. The topic which I told is pending is actually removed. It's not there. And that, 1 minute. Yeah. So the topic that I told is pending is displacement current, and displacement current is actually not there. So we need not discuss about it. So to conclude this chapter, electromagnetic waves is over actually. It is the smallest chapter in your physics. Generally, we complete in 1.5 hours. We took 2 hours of time, and yes, this chapter is over. Okay. To just give you a summary of what we have discussed, electromagnetic waves, introduction is what we discussed. What are electromagnetic waves? Then the displacement current topic is eliminated. Right. So since displacement current is not there, this since displacement current is not there, this is not there. This topic is not there. And we have seen what is the source of an electromagnetic wave. We have seen what is the nature of electromagnetic wave. We have discussed what are the properties of electromagnetic waves. And we did some problems also. I told you this problem is not required. And electromagnetic spectrum alone, I gave it as self-study. Right? So from the electromagnetic spectrum, the important point that we need to carry forward for the next chapter is the concept of visible light. So if you look at the concept of visible light basically has the wavelength between 400 nanometer and 700 nanometer, where 400 nanometer corresponds to violet light and 700 nanometer corresponds to red light. The combination of all these things put together is called as white light. This you would have learned in the concept of spectrum, right? That is the dispersion of white light when it is passed through a prism. Right, we know that white light comprises of 7 distinct colors. See, 7 colors is what we are able to see. There will be other wavelengths also, which we are not able to see. They are mixed up. Okay. So, keeping all these points in mind, let's get started with the next chapter, that is ray optics and optical instruments. So, this is the chapter we are going to start with, which is the first chapter of your second volume book. Okay. So there is an extension of what you have already learned in your 10th standard, except the fact that you'll be learning certain proofs also. Okay. So just give me a second. I'm opening my notes. See, the chapter 9 is called as ray optics, or sometimes it is also referred to as geometric optics. You can ask me what is the reason for it? Because most of the problems or solutions to the questions in this chapter are solved using geometry. That is why we call it as geometric optics. So first, let's see the basic introduction that is required for this chapter. So introduction is, first is we need to understand what does optics mean. So what does optics mean? Optics is one of the branches of physics which deals with the behavior of light and other electromagnetic waves. So we are saying ray optics. No, optics is the branch of physics which deals with the behavior of light and other electromagnetic waves. Next is, we need to understand what is light. So light, we know light is an electromagnetic wave, or you can also call it as radiations, whose wavelength. So this light I'm trying to talk about is visible light. Okay, whose wavelength ranges from 4,000 angstrom to 7,000 angstrom, or 400 nanometer to 700 nanometer, to which the eye is sensitive, is called as visible light. Okay. So there is some important note that we need to make. If you look at the name of this chapter, it is ray optics. If you look at the name of the next chapter, it is called as wave optics, or sometimes it is referred to as physical optics. Okay. So in the present and the next chapter, we will be studying the behavior of beam of light only. In this chapter, next chapter, will be concerned only about light. Okay. So what will that light do? That light will encounter some simple optical devices like mirrors, lenses, and aperture. Aperture means openings. Okay. So what happens is, there are two things that we need to take into consideration. First, tell me one thing. What is the speed of light? It is 3 into 10 power 8 meters per second. So when the speed of light is more, can I say its frequency is more and its wavelength is less? Etc. Okay. So if there are certain scenarios where the wavelength of the light is negligible compared to the dimensions of the devices like mirrors, lenses, and all those things, in those cases, light is considered as a ray. That is, in this chapter, compared to the size of the objects with which light is interacting, it is going to interact with mirror. Mirror is going to be in terms of few centimeter, whereas the wavelength of light is in terms of nanometer or angstrom. Since the wavelength is very, very, very small compared to the objects with which it is interacting, then light can be considered as a ray, which is governed by some simple geometric rules. Whereas in the next chapter, what will happen is the light, okay, whereas in the next chapter, the wavelength will not be negligible compared to the dimensions of the object, because you'll be dealing through very, very, very small openings. Maybe the opening will be of this size. Okay. What will happen when light is passing through this kind of an opening? Opening is also small, wavelength of light is also small. During that time, light is considered as a wave. That is why we have wave optics or physical optics. So I hope you guys are able to understand the difference. So in this chapter, we will consider light as a ray due to what reason? What is the reason due to which light is considered as a ray in this chapter?
Wavelength, when compared to the dimensions of the device, is negligible.
Yes. Perfect. So during that time, you can consider it as a ray. Since you're taking it as a ray, you can take the help of geometry to solve the problems. Okay. Next is, there are certain phenomena that is exhibited by light. What are they? One is reflection, the next is refraction, right? So the total internal reflection, all these things are there. So first phenomenon that we are going to see is reflection of light. So what do we mean by reflection of light? So it is a phenomenon. Phenomenon is something which you can see. So phenomenon in which the light ray is sent back into the same medium from which it is coming. On interaction with whom? On interaction with the boundary, and generally that boundary will be a smooth and a shiny surface. Okay, that is what we call it as reflection. Okay, so the boundary can generally be a rigid surface or an interface between two media. For example, the surface of water is a reflecting medium. Sometimes what happens, if the water is clean, right, you take your face close to it, you can actually see the reflection of your face in it. But water is doing what? The water surface is separating the air and the water medium. That is what they have mentioned in the point. Interface between two media. Okay. So I hope you guys are clear with reflection of light. Now the question is, which objects have the tendency to reflect the light?
Okay.
Uh, Generally mirrors, right? So if you talk about a boundary where one side of the boundary is transparent, but the back side of the boundary is opaque. If you have this kind of a scenario, then this boundary has a tendency to reflect the light. Okay. Now, generally we discuss about mirrors. That is why if you see the part of reflection of light, we'll concentrate more on mirrors. Now we'll discuss about the laws of the reflection. So what are the laws of reflection? So
The
before,
first one is the incident ray, reflected ray, and the normal are all in the same plane. The second one is angle of reflection and angle of incidence are same.
that's right. So before that, we need to know what is the angle of what is the meaning of angle of incidence and what is the meaning of angle of reflection. So if I take a boundary or an interface, if I take a boundary and there is a ray which is hitting the surface. So what is the name of this ray? Obviously, it's called as the incident ray. What is this point called as?
Point of incidence.
Point of incidence. So incident ray is there, point of incidence is there, right? At the point of incidence, whenever you're trying to draw the ray diagram, the first thing that you need to do is draw a line like this. What is the name of this line?
Normal.
Normal. So normal generally means perpendicular. Perpendicular to whom? Perpendicular to the reflecting surface. So if you're able, so this is the incident ray. If you're able to measure between the angle, if you're able to measure the angle between the incident ray and the normal, then that is called as the angle of incidence. Now, what will happen to the reflected ray? It will start reflecting back in this direction. Let's say with an angle of reflection R, then the incident ray, reflected ray, and the normal all are said to be lie on the same plane, and the angle of incidence is equal to the angle of reflection. Okay. So incident ray, reflected ray, and normal all lie in the same plane. Angle of incidence is equal to angle of reflection. So laws of reflection are applicable to any kind of a reflecting surface. This is an important point to be noted. Okay. Now I have created some notes on how to draw a normal for any reflecting surface. See, generally there are two kinds of reflecting surface. One is a plane surface and the second is a curved surface. The curved surface is what we technically call it as spherical surface. So when you talk about a plane surface, first draw the incident ray onto the reflecting surface, and at the point of incidence, with respect to the reflecting surface, draw a perpendicular, generally dotted line to the surface, which will give you the required normal. So if you take a plane surface, you draw the incident ray first. At the point, draw a set of dotted lines which are perpendicular to the normal, perpendicular to the surface, and this dotted line is what is called as the normal to the surface. Whereas with respect to a spherical surface, when you talk about a spherical surface, the important point with respect to the spherical surface is the center of curvature. So when you draw an incident ray parallel, for example, any incident ray, then at the point of incidence, you need to draw the normal. With respect to a curved surface, that is a spherical surface, the normal will always pass through the point of incidence and the center of curvature. You just need to join them. This will be called as the normal. Okay. I hope you guys have made a note of this. Okay. So diagrammatic representation, this is what is normal. Then this angle is called as angle of incidence. This will be called as the angle of reflection. Similarly, with respect to a concave mirror, also do the same thing. If you draw a line parallel to the principal axis, what will happen? This will be the angle of incidence and this will be the angle of reflection. Clear? Is there any doubt, guys?
No, sir.
Okay. So now we will see reflection from a plane surface or a plane mirror. Now tell me one thing. You know, you have already learned how to draw the ray diagrams, right? So when I talk about the ray diagrams, there are certain rules to be followed. The ray diagrams will help you to understand whether the image formed is a real image or a virtual image or something like that. Correct? So with respect to a plane surface or a plane mirror, how will you find whether it is a real image or a virtual image?
I think if you pass the light from one side and the image is formed on the same side, it is a real image, and if it is formed on the other side, it's a virtual image.
Perfect. Right answer. So does a plane mirror form a real image or a virtual image?
Virtual.
Correct. It forms a virtual image. Let's see how it forms. Okay. So if I take a plane mirror like this, then there are two objects that I've considered. One is a point object and the second is the extended object. If you take a point object, okay, with respect to the point object, if I take the first incident ray like this, then at the point of incidence, I will draw a normal. Then this angle will be called as the angle of incidence. Then what will happen to the reflected ray? The reflected ray will make the same angle with respect to the normal and get diverged away. Right? So for us to draw the ray diagram, we need minimum two reflecting rays. So the other incident ray is considered symmetric with respect to the first. When you do that, it is going to hit the surface and it will start reflecting back in this way. Okay. This reflected ray and this reflected ray will never meet each other because they're getting diverged away from each other. So when they're getting diverged, what are we supposed to do? Elongate them in the backward direction and they will meet at a particular point on the principal axis. And this is where the image is formed. Since the object and the image are on opposite sides, what are all the conclusions you can draw? One is it's a virtual image. Can you speak something about the magnification? In this case, can you speak about magnification?
It's a point size, right?
Because it's a point-sized object, you cannot speak about magnification.
Same
right?
size. That's the first.
It will be same size. That's all. It will be the same size as that of the object, right? And the most important thing is, if this is the object distance and this is the image distance, object distance is equal to the image distance. Means it is exactly formed at the same distance behind the mirror. Okay, that is one thing. Second is, if you take an extended object, what do you mean the extended object? If the object has a finite size associated with it, then what we can do is, you take one of the rays incident on the mirror, normal to it. So what is the angle of incidence here?
90. 0, 0, 0.
Angle of incidence is 0. So when you say a ray is incident normal to the surface, don't look at the word normal and get confused. The incident ray itself is a normal. So what will be the angle between the same lines? It is 0 degrees. Okay. So the reflected ray will retrace its path. Secondly, if you consider another ray parallel, if you consider another ray like this, at this point you draw a normal, right? Then this will be the angle of incidence. Then what will happen to the reflected ray? It will also make the same angle with respect to the normal, right? Then what will happen, guys? This first reflected ray and the second reflected ray will get diverged away from each other. Again, they have to get extrapolated in the backward direction for you to get the required answer. So if h0 is the height of the object and hi is the height of the image, what will be the relation between both? h0 will be equal to hi. In this case, yes, you can find the magnification. If you remember what is the formula for magnification, it is the size of the image to the size of the object and it comes out to be 1. I'm not using sign convention here. We'll discuss about the sign convention later. But the magnitude of magnification in this case is going to be 1. And here also the object distance and the image distance are the same. Yes. So there is one important property that a plane mirror will exhibit. What is it? There is one very important property that a plane mirror will exhibit. What is it?
So is that the size is always the same. Oh.
Lateral
inversion.
So the important property that a plane mirror exhibits is the lateral inversion. Right? So everybody knows what is lateral inversion. Right. So I just wanted to write down what is the definition of magnification also. It is defined as the ratio of the size of the image to the size of the object, and m is equal to hi divided by h naught. It is also termed as linear magnification. See, there are different kinds of magnification: linear magnification, circular magnification, aerial magnification, something like that. And you have angular magnification. So if you discuss about the ratio of height of the image to the height of the object, we call it as linear magnification, and it is generally a dimensionless one. Okay. Next. When you talk about spherical mirrors, now we are done with plane mirrors. Okay. When you talk about spherical mirrors, what comes to your mind? So spherical mirrors are named, they are given that name because they are formed by taking a part from the spherical surface. Mirrors which are a part of the spherical surface are termed as spherical mirrors. What are the two types of spherical mirrors that you guys already know? One is concave and second is convex. So concave and convex are named based on the shape of the reflecting surface, correct? So if it is curved inwards, then you call it as a concave. So concave mirror is also called as converging mirror. Why it is so, we will see it later. Similarly, for a convex mirror, where is it polished? It is polished on the inner side. So it is also called as a diverging mirror. So mirrors silvered on the pulse side and depressed side acts as reflecting surface is called as concave. And mirrors silvered on the depressed side and the bulge side acts as a reflecting surface is called as a convex mirror. Okay. So now we will see some terms and definitions that are related to spherical mirrors. Shall I proceed? Yeah.
Yes, sir.
So the first term that we need to know is center of curvature. So what do you mean by center of curvature? Why is no one else participating in the discussion? You guys don't know or you forgot everything? Yeah, Nicholas, tell me, what is center of curvature?
So the spherical mirror is a part of a sphere. So the
Correct.
center of that sphere is the center of curvature.
Correct. So if you take the spherical surface, see, it's actually a part of the sphere, right? So the sphere will have a center associated with it. The center of that sphere from which this mirror is taken is called as the center of curvature of this mirror also. That is first point. Okay. So center of curvature for a concave mirror is on the reflecting surface side, and for a convex mirror, it is on the silvered side. Correct? It is on the silvered side. That is on the depressed side. So this is one important point to be noted. You can ask me, is this important in terms of statement? Yes, it is important because you need to understand the sign convention. Okay. Next, what is a pole of a mirror? So you have a mirror surface. You have a mirror surface. If suppose the length of this mirror along the curvature is L, and if you are able to find a point such that the upper part is L by 2 and the lower part is L by 2, then that center point is what is called as the pole of that particular mirror. So center of the mirror surface is called as pole. Okay. Now the next term that we need to know is principal axis. Axis is what? Axis is a one-dimensional shape. So what does the principal axis mean? It is an imaginary line that is passed through the center of curvature and the pole. So if you're able to think about the imaginary line passing through the center of curvature and pole, that is what we call it as principal axis. Then what is aperture optics? So if you are able to take a scale and measure the linear distance between the points A and B, that is called as the aperture. Sometimes it is also referred to as the diameter of the lens. Okay, diameter literally doesn't mean 2 times the radius of curvature. No. So diameter here means it is the distance between the points A and B. That is the end points of that particular spherical mirror. I hope I'm clear.
Yes.
It's called as the diametrical length. It's also called as aperture. This is a new term that you're learning today. Next is radius of curvature. Name itself is telling. The radius of the sphere from which this lens is taken is called as the radius of curvature. That is one way. Or the distance between the center of curvature and the pole is also called as radius of curvature. Now, the next important term that we need to focus upon is principal focus. Can you tell what is this? Can you guys recollect and tell me what does the principal focus mean?
If we make a parallel beam of rays pass to a curved surface and curved mirror, spherical mirror, then it will all meet and all the rays will meet in a specific point, and that point is principal focus.
Yes, that is right. What is that point and where will that point lie?
It's point on the principal axis.
R by 2.
Correct.
Between,
that we will see. Why it is R by 2, all those things we'll see. So generally the observation shows that when you consider a narrow beam of rays which are parallel and near to the principal axis. So if you are able to talk about the rays which are parallel and closer to the principal axis, they are generally called as, any idea about what are the rays closer to the principal axis called as? They are called as paraxial rays. Please write it down. So if you consider a set of rays parallel and near to the principal axis, what will happen? They get reflected back from a concave mirror so that all the rays converge and meet at a point F on the principal axis, which is termed as the principal focus of the mirror. So what we are trying to say is, if you have a concave mirror in your hand, it has a real focus. Whereas when you talk about a convex mirror, I will draw and show it, don't worry. Whereas when you talk about a convex mirror, what will happen is, it has a virtual focus. Okay. So what I'm trying to say is, with respect to a concave mirror, if you consider a ray parallel to the principal axis, so what is the name of the ray that I've drawn now? It's called as the incident ray. So this is the point of incidence. So how to draw the normal? Join the center of curvature and
point of incidence.
If I take this point as A, then this angle will be I. Then the reflected ray will make the same angle I. I wrote it as R, but it will make the same angle I with respect to the principal axis, and it will get reflected. Similarly, if you consider another incident ray like this, okay, after reflection, it will pass in this way. Am I right? So this is the second normal that we are trying to talk about. So these two reflected rays will meet at real time. They get converged. That is the reason why we call concave mirror as a converging mirror. So they meet at a point on the principal axis, and that point is what is called as the principal focus. Whereas with respect to a convex mirror, what will happen? If you take a ray parallel to the principal axis at the point of incidence, you will draw a line like this. So this will be the angle of incidence, and this ray will get reflected away from the mirror in this direction with an angle of reflection R. Similarly, if I consider another parallel ray at the bottom, but remember these rays should be closer to the principal axis. Okay, there is something called as aberrations that will occur. Aberrations in the sense there will be some errors that will occur if the rays are considered far away from the principal axis. Okay, but I'm not getting into those details. But yeah, so these rays should be closer. So they are called as paraxial. I thought you guys will ask me what are the names of the rays which are away from the principal axis. Any idea about what are the rays away from the principal axis called as? They're called marginal rays. So marginal rays are the ones which are away from the principal axis. Paraxial rays are the ones which are closer to the principal axis. Okay. Now, if this light gets reflected like this, then the first reflected ray and the second reflected ray are getting diverged away from each other. Hence, you need to extrapolate them, extrapolate in the sense, extend them in the backward direction so that they tend to meet at a point on the principal axis, which we call it as the principal focus. So principal focus with respect to a convex mirror is virtual. It is not real. It is like as if the rays are coming from there. Right? If I extend it, is it not looking like as if these reflected rays are actually coming from the focus? Right? Now I hope you understand why convex mirror is called as a diverging mirror. Am I right? Am I clear, guys? So now you understood what is the meaning of principal focus. So if anybody asks you to locate the principal focus with respect to a mirror, you need to consider the paraxial rays and locate the position by drawing the ray diagram. Okay. And the last point that we need to know is focal length. So what is focal length? The distance between the pole. See, generally, if you take it like a two-dimensional geometry, right? Pole is taken to be the origin. All the distances are measured with respect to the pole only. So the distance between the pole and the focus is what we call it as focal length. Okay. So what is the relation between the focal length and the radius of curvature? Focal length will be equal to half of the radius of curvature. Why it is so? We will derive it. Don't worry about it. We will try to derive and understand why it is so. Okay. So marginal rays, rays which are away from the principal axis are termed as marginal rays. Paraxial rays, rays which are close to the principal axis and make small angles with it. Right, are called as paraxial rays. So one important note to be made is in this chapter, whatever we are dealing, whatever derivation we are going to do or something, all the discussions are related to spherical mirrors and will be restricted only to paraxial rays and mirrors of small aperture. Okay, these are the two important things we are going to take into consideration. Why it is so? Because when you consider the mirrors of small aperture, the angles are going to be very, very small. Okay, when the angles are small, then sine theta can be approximated to theta can be approximated to tan theta. This is the reason why we consider these kind of structures. Is it clear? So now I'm going to explain how the relation between the focal length and the radius of curvature is exactly r by 2. Shall we start?
Yes.
So that is going to be the last topic for the day. Next class, I will start images formed by spherical mirrors. So please make a note. I think this is the first point you're going to write today. So the heading is a relation between F and capital R. Okay. See, for diagrammatic purpose, I'm taking the lens to be big. But what did I say? The lens that you're considering should have a smaller aperture. When you have a smaller aperture, see, for example, I'll tell you there are 2 points AB and A dash B dash. A dash B dash is also a part of a sphere only. Out of AB and A dash B dash, which one has smaller aperture?
AB has a smaller aperture.
A dash B dash. So when A dash B dash has smaller aperture, tell me one thing, how is this curvature looking like? So when AB is there, right, the curvature is more. Whereas when A dash B dash is there, the curvature is very small. Correct? So if I take another point in between A double dash and B double dash, the curvature becomes even small. That the curvature can be approximated to a straight line. You're able to understand what I'm trying to say?
Yes, sir.
Okay. So the reason why we are trying to approximate it to a straight line is because we want to apply geometry and trigonometry to solve these problems. That is the reason why we consider paraxial rays and mirrors of smaller aperture. Okay. if I take this to be the pole, or if I take a ray parallel to the principal axis, this ray after reflection will pass through the focus. Okay. And here is where you have the center of curvature. If I take this angle as theta, this angle is also theta. Now, what is angle AFP equal to?
Angle AFP is 2 theta.
Correct. Alternate interior angles. So AFP will be equal to 2 theta. Right. So this is 2 theta. Then how much will this angle be? What is angle AFC equal to? That's a very linear pair. Huh?
Yes, will be 180 minus 2 theta.
It is 180 minus 2 theta. So angle ACF plus angle AFC plus angle CAF put together is 180 degrees. Accept it. So what is the angle ACF? If I take, so that is what we need to find. Angle ACF plus what is the angle AFC? 180 minus 2 theta plus angle CAF is theta is equal to 180. 180 and 180 will get cancelled. Angle ACF will be equal to theta. So this angle is also theta. Accepted, guys? No.
Yes.
So what is the distance between the pole and the focus? It is a focal length. What is the distance between the pole and the radius of the center of curvature? It is the radius of curvature. I told you AB is of smaller aperture and this ray is considered closer. So this is a paraxial ray. Correct? So can I say APF, if I take this as 2 theta and this is F, can I say AP divided by PF is equal to tan 2 theta? Correct? AP divided by PF is tan 2 theta. But I told the angles are very small. The tan 2 theta can be approximated to the angle itself, 2 theta. Let me call this as equation number 1. Similarly, if I take the triangle APC, this is theta and this is R. So what is AP divided by PC equal to? It will be AP divided by R, which is equal to tan theta, which can be approximated to theta. So here it is AP divided by PF is how much? F. See, to be more specific, right? Whenever you're doing any derivation in this chapter, you need to take the sign convention into consideration. So I told you, right? Pole is taken as the origin. Anything measured on the left, any distance measured on the left of the pole is generally taken as negative. So this should actually be minus. This should also be minus. I hope I am clear. So theta is equal to minus AP by R, where theta is in radian. 2 theta is equal to minus AP divided by F. I will take this theta and substitute it here. So 2 into minus AP divided by R is equal to minus AP divided by F. Minus AP are gone, which implies cross multiply 2F will be equal to R or F is equal to R by 2. Did you understand, guys?
Yes, sir.
R by 2 is applicable. Yeah. F is equal to R by 2 is applicable for what kind of mirrors? Mirrors with smaller. See, this can be an assertion reason based question. So F is equal to R by 2 is applicable only for mirrors with smaller aperture and what? And only when you consider the focus being formed by the rays which are paraxial in nature. So this is what the basic is. Okay. I hope you guys have made a note of this point.
Yes.
Yes, sir.
So this is all about the relation between the focal and the radius of curvature. So I cannot put so much information to your brain on a single day. So next class, what we will do is we will discuss about how the images are formed. So if possible, you open your 10th standard textbook, go through the concepts and come, so that our job is easy. What are all the different steps to be followed to ensure you complete a ray diagram? Once that is over, you have a mirror formula, right? What is the mirror formula, guys? You remember? 1 by V plus 1 by U
plus 1 by U.
1 by M. Maybe in the 10th standard, you would have applied sign convention, found the answers, magnification, all those things. But thing is, now we will see how this formula has actually come and how to apply this formula to solve the problems. Once that is over, we are done with reflection. Then we are good to go with the refraction concept. Okay. See, this chapter alone, I'll be doing a lot of problems. I'll be giving different assignments and I'll be doing a lot of problems. So you guys have to work along with me. Okay, but I promise I'll go slowly only. Since there's a term to portion, I'll go slowly only. That is the reason why I'm stopping with 45 minutes, 50 minutes. Okay. So that you don't take any pressure about it. Just work with me. That's it. That's more than sufficient. Okay. Any other doubt, guys?
No, sir.
No, sir.
Yeah, that's good. Then we are good to wind up. Okay. I'll see you all on Monday.
Thank you, sir.
Thank you, sir.